So welcome to today's webinar. And as Mikko said, the theme is sustainable system transition. And it will be from a slightly theoretical perspective. The themes of today are first starting with what is a system, how to define it, how to set the boundaries for a system. What is systems thinking and how it can help us with problems of today. And then we're going to look at the climate crisis as a systemic problem and how to deal with the climate crisis from a systemic thinking perspective. We're also going to have a 15-minute break at some point during the webinar. Not sure if it will be exactly at that point, but we will see. Then we will also, of course, go into like how to bring about systemic change. And then at the very end, looking at some homework or some exercises that you can do in your own time. I've already been been the speaker of 2 webinars so far in this lecture series, but if someone is joining us for this webinar today, my name is Aura and I work as a sustainable development specialist in Sykli. My background is in forest science and environmental science. And I have special interests in kind of handprint thinking. So instead of your footprint, increasing your handprint, and different kinds of sustainable future thinking and systems thinking. In my free time, I do martial arts and acrobatics, and I love spending time in nature. And if you would like to connect, there's my Twitter and LinkedIn details. Systems thinking for me, what the kind of big thought that told me what systems thinking is I came across this saying, which is a Chinese saying, give a man a fish and you will feed him for a day. Teach him how to fish and you will feed him for a lifetime. And now a systems thinker starts thinking, okay, this is a good start, but there's more. What if this man does not have money to buy fishing gear? Or he does have fishing gear, he has a fishing rod, but his neighbor has a trawler, or he doesn't live close to water, or we teach one person how to fish, but we are 7 billion people who then still don't know how to fish. And then if we teach everyone, what if there are not enough fish for everyone? So the Chinese proverb is a good start, but it's still on quite a small scale. It's one step from one step further, but there are a lot more steps that we can take as a systems thinker to actually solve the problem of giving the man a fish. What we really want to achieve is how do we feed everyone today and in the future? And education is, of course, a very good tool in changing systems, but it might not be enough. Okay, so first we start with what is a system. Here are a few definitions. A system is a group of interacting, interrelated, interconnected, or interdependent elements that constitute a complex and integrated whole. So this idea that there are a lot of elements that then interact together and work as a whole system. The system is an interconnected group of elements coherently organized for a goal. So this definition adds the idea of the system having some sort of goal. And lastly, a system is a group of essential parts or subsystems that can affect the behavior and properties of the whole system, and none of which has an independent effect on it. So this maybe puts it, goes a bit deeper into what a system is and how the elements relate to each other. And systems are often relative. The systems do not exist independently of an observer. So it's the observer of the systems who kind of uses systems thinking to indicate something which to the observer looks like it's put together in a coherent way. And usually we do this by distinguishing the system from other systems that are then not interconnected to it. And the observer is kind of outside of the system, kind of they're in the environment on the outside and then observing the system. So this means that they are always relative to the environment. On Wikipedia, a system is defined as a group of interacting or interrelated elements that act according to a set of rules to form a unified whole. So this definition introduces the idea of rules. So these interconnections kind of bring about rules and bring about something that follows these rules, and then something happens according to these rules. And as a systems thinker, you are trying to find out what those rules are. Then adding on layers still on top, a system surrounded and influenced by its environment is described by its boundaries, structure, and purpose, and expressed in its functioning. So now we are introduced to the term of boundaries. So of course, a system can grow so large that it's not anymore practical to think of it as a system, and there's no way that we can get any information out of it, even with a systems thinking method. So it must have some sort of boundaries, and defining those boundaries is an essential part of systems thinking. Within the boundaries, it has structure, and the rules that were in the previous definition, they bring about a certain kind of purpose and a certain kind of functioning. And lastly, what the term system comes from is from the Greek term systema, meaning being put together. And actually, I already covered this. So the system does not exist independently of an observer. And it's thought that to the observer, the environment that is outside of the system is less orderly and more complex than the system which the observer is looking at. And when you think of something as a system, it's you take a very complex set of interrelations and you try to bring some order into that and reduce the complexity so that we can do something with the system. And since the systems imply order, they refer to something that is in a certain way seems more than the sum of its parts. I think this saying is familiar to all of you, that something is more than the sum of its parts. And then lastly, systems are a way of looking at the world. It's very different to say that the world is a system. I don't think we can say that. But what we can do is look at the world as if it was a system. And the systems aren't kind of out there in the world waiting to be studied. We also create the system once we start using systems thinking to some kind of problem. For example, there is no such thing as the climate system. It's just a lot of interacting thermodynamic and chemical processes, and then we choose to call it a system and name all of its parts and treat it as a whole with boundaries. And it's very convenient, but like it isn't a system until we call it a system and treat it as a system. Here's a visualization of those previous definitions. So we have the environment, then we have the boundary within which we have elements of the system, and then the various interconnections in that system. No system can be completely closed. There is usually some kind of input and some kind of output. And this is where this defining the system boundary becomes very important. But hopefully this visualization can help you understand what systems are, what it actually means to apply systems thinking to something. The elements can be tangible. They can be like trees, nutrients, workforce, or they can be intangible like knowledge or a brand. And when we start thinking of something as a system and we try to start identifying the elements, we start using reduction, and basically we can use it in a never-ending process. So reducing the elements into sub-elements and sub-sub-elements and so on until we have so much information that it doesn't actually help us in understanding how the system works or understanding how we might affect that system. I think the most important thing in a system are the interconnections. So usually it's quite easy to come up with the elements of a certain system, but the interconnections are more important for the functioning, more important for the character of the system, and also for trying to make change. We have physical flows. That interconnections can be physical flows like nutrient flows or people moving around, or they can be informational flows like communication, decision-making, influencing decision-making, these kind of things. And once we start identifying elements and interconnections, we we bump into this kind of an effect that there are so many, basically millions of elements and infinite connections, and it's not very helpful. That's why we need to choose a boundary, and then we need to identify how open or closed the system is. And usually choosing the boundary is a matter of judgment, so it's up to the observer. And an open system means that you have different kind of flows that come into the system and flows that go out. And a closed system is usually the only input and output is energy. So you can think of a closed system. In the picture, you have like this pot with a lid on top. So that's a closed system. What happens within? You can still have energy going into the pot and going out of the pot, but the system is still considered closed. The lid is closed. And then the open system is like the pot with the lid off. So there is both energy flow, but also material flow in the form of, for example, water vapor, or they could be other things. There could be food coming out or something. But this is an open versus closed system. And once we have the input to a system and we have the rules, the system structure, out comes system behavior. And the system's behavior is part of its identity, and it is observable over time and under different conditions. So systems that are structurally similar exhibit similar patterns of behavior. And also this means that regardless of the kind of starting point, the system will show similar patterns and eventually kind of find a certain kind of state on the inside. And the system behavior can be seen as changes over time or different kind of dynamics that can be seen in the values of these Usually the elements are different kinds of variables that have values. For example, trees are an element of the forest system, and they have the variable could be, for example, the volume of trees, and the volume of trees changes over time according to certain kind of dynamics. And some system behaviors are desirable and some are not. And yeah, usually just adjusting the initial input values won't change the output that much, unless it's a very radical change, which also then has certain kind of knock-on effects then within the system structure. A system also has a purpose or a function, and there are two kind of purposes, which are not very cleverly named because it's easy to get these mixed. There are purposive or purpose-built systems. For example, we build a factory and it's built for a purpose and we know how it works. And then a system can also be purposeful, having multiple purposes. And for example, human societies are such purposeful systems. So there are many different goals, for example, within the system and its elements. And maybe kind of a recap of characteristics of a system. So it's not just a collection of elements. These elements affect each other and affect each other in a very specific way. They are organized in a specific way to achieve a system's purpose, which is kind of very easy to see in, for example, a factory, but then not so clear in human systems. Systems have feedback, so the interrelations have different kinds of feedbacks, and I'll get back to those in a bit. And sometimes easy solutions can lead to negative impacts elsewhere. So if we think of our planetary system and think about climate change, and we want to optimize carbon capture, and then we start planting monocultures of trees that capture as much carbon as possible, we are going to lose a lot in biodiversity. Also, if you think about unintended consequences, for example, in ecology, trying to deal with populations that have grown too big. For example, in Australia, there is an outbreak of a lot of animal species that have been brought over from Europe. And since they had no natural predators in Australia, the population exploded. And then humans tried to solve the problem by bringing in predators, but then they ended up eating the native species and not actually the invasive species that it was intended to solve. So now instead of one problem, you had two problems. So it's really important to, when you try to influence a system, to have a look at the interrelations and think whether there might be some unintended consequences that come out when you change a certain input, or whether you insert something in, like a new element and into the system. So in this way, systems thinking would have been a very good thing to do before introducing invasive predators onto a new continent. In a system, cause and effect are not closely, or might not be closely related in time and space, which means that systems can be very difficult to measure. And then if we change something and we don't see any output change for some while, we might think it's not working, but in reality, there are just delays in the system or feedback loops that make it so that the cause and effect are not closely related in time. And climate change is a very good example of this, because We have been emitting more and more carbon into the atmosphere since the Industrial Revolution, and only now are we starting to see the more severe consequences, because we have had certain buffers in the system, such as the ocean, which are which have acted as buffers. And now we have also perhaps gone over some threshold points that then suddenly accelerate climate change. So there might be these kind of buffers and these kind of unintended emergent properties that come out of the system with a delay. And that makes them hard to see. There are two kinds of feedback loops. If we simplify, there are two kinds of feedback loops. Of course, in reality, the feedback loops have different strengths, and various feedback loops can work at the same time. But in a simplified way, there are two kinds of feedback loops in systems. The first is a balancing feedback loop, and this can be visualized with like a bowl, or like a ball that's in a bowl, that even though you put a new kind of input, the ball will always come back to its equilibrium. And this is a balancing feedback loop. Then we have the reinforcing feedback loop, which is kind of an equivalent of the snowball effect. And it can be, for example, exponential. And then we can have like several kinds of feedback loops working at once, bringing about different kinds of patterns, such as having various equilibrium points. So we might start on the left of this new graph, and then if the inputs only change slightly, we will remain in the first equilibrium point. But if we're pushed over the first threshold, we'll find ourselves in the next equilibrium point. A lot of patterns in nature, they might start off with a reinforcing feedback loop, and then once it goes over a certain once a variable goes above a certain number, then it will go into the balancing feedback loop phase. And the reinforcing feedback loop, it cannot go on forever. We need the balancing feedback loops to kick in at some point. And human beings were very used to thinking in terms of linear sequences and of cause and effect. For example, A causes B, which causes C, and so on. So we can have chain reactions, but we still think of them as linear. But our interactions with the world are rarely like this. And many times the change can feed back on itself in some kind of way. These loops are also sometimes called positive or negative loops, but I don't think that those are very good terms, because they kind of imply whether things are good or bad. But basically, the reinforcing loop is a positive, and the balancing feedback loop is a negative. But we need the balancing loops. That's why I don't really like to call them negative feedback loops. And of course, the reinforcing feedback loop is good when you want to achieve change. For example, your post goes viral. That's usually some kind of, or that's a reinforcing feedback loop. You kind of get above a threshold of a certain amount of people liking or sharing or commenting in a post, and then suddenly it goes off on a reinforcing feedback loop pattern. Of course, that then also dies down at some point. But then you can also, reinforcing feedback loops can be bad. When you don't want the change, for example, a forest fire that's spreading, or disease, or climate change. And yeah, the balancing loops keep our systems in kind of a stable state. And of course, even when we want to achieve change, we kind of want to achieve a new stable state. So we want to make change with a reinforcing feedback loop, but then find a stable state where the balancing feedback loops are in operation. And of course, in real life, all these curves and graphs are never this simple. This is the temperature of planet Earth in the past 542 million years. And what's remarkable about this graph is that the climate has been relatively stable for the last 10,000 years since the end of the last ice age. And over that time, the temperature has varied less than 1 degree. And this suggests that there are some kind of balancing loops that have been in play in the past 10,000 years, meaning that the incoming energy from the sun and the outgoing energy lost back into space has been stable. Now, this has been the global greenhouse gas emissions in the past 260 years. And as you can see, this very much looks like the reinforcing loop. And this could be an example of this reinforcing loop. So burning fossil fuels has led to economic development that has led to an increased demand for energy, which has led to increasing burning of fossil fuels. Of course, this is a fairly simplistic example, but anyway, this illustrates how a reinforcing loop works and how it could have been working on this on the global greenhouse gas emissions in the past years. And now, like I said, there always must be a balancing loop, and it will kick into play at some point. Now there's somebody's microphone is on. Maybe Mikko can mute them, please.
Just a second, I'm trying to find the, yeah, cool.
Thanks.
Okay.
So yeah, here's an example of the balancing loop that could kick into play, but clearly hasn't, even though the price of fuels has risen in the past months, and even before that it has been rising. This balancing loop clearly hasn't kicked in yet in the system, because the reinforcing loop is still very dominant. And but at some point, some kind of balancing loop will come into play. The question is, what kind of stable state will we be in once what kind of state will we be in when the next stable state is found? Like if the temperature is a lot higher, say 3 degrees higher than it is now, those are temperatures that humans have never experienced before. And the next stable state might be such that it cannot support human life as we know it. But we're working on this to make the next stable state such that it can support human life. Here is an example of kind of feedback loops and what kind of system relations can be in play. So this is the current situation where our economic activity, or our GDP, is dependent heavily on resource use, and as such also emissions. So at the moment, the decoupling of GDP from resource use or emissions has not been done anywhere in the world. These two variables are very much kind of married very tightly. What we are trying to achieve is to find leverage points where we can kind of access the system and change so that we can disrupt the loops that keep GDP and resource use married together. And this graph shows relative decoupling, which means that the GDP is growing more than the resource use is growing or the emissions are growing. However, resource use is still growing and emissions are still growing in this scenario. So it's not sustainable in the long term if we want to achieve a stable state where this planet can support human life. And then what we really want to achieve is absolute decoupling of the GDP from resource use or emissions, for example, through circular economy. And currently we have a lot of feedback loops that are preventing this from happening. And what kind of feedback loops are preventing this? Well, we currently live in a very linear economy, and our economic model is such that you get most economic gains from a linear economy. You get most economic gains from selling more stuff. And even though we have some circular solutions, currently those are not dominant because the linear economy still is the way to get most economic gains. And how to disrupt this kind of feedback loop, we really need to very heavily disrupt our economic system so that it will be more viable to be in the circular economy. Companies will get more economic gains out of circular economy than they do out of linear economy. And this has to happen on a global scale. Okay, next I will introduce what kind of types of systems we can have. We can have natural systems such as, well, the planet Earth. That's a very big system, but also it has fairly kind of clear boundaries. We can also look at only the Earth's atmosphere as a system and put the boundary such that we only take interactions with the atmospheric layer, but these are natural systems. Or a forest can be a natural system. Then we have designed physical systems, which are perhaps the most easy ones to comprehend, such as a factory. Then we have designed abstract systems, such as, for example, language. Then we have, sometimes these are grouped together, the human activity systems or the social systems, but they can also be thought as separate, or different types of systems. So human activity systems are, for example, consumption or learning, and a social system can be like a sports club. Now comes the first short exercise of 10 minutes. Try to think of an example of each type of system and then share them in the chat, or just note them down for yourself, or then just like have a short think about what different kind of systems you can think of. And I will actually put the previous slide. So try to think of one of each of these 5 systems, or at least come up with like examples that what you see as a system. And we'll maybe take 5 minutes in this case, not 10 as I have on the slide. I can give another example of different or systems that can of these different types. So for example, a social system can be a family, and the boundaries can be very different in different cultures. So, and the culture itself is kind of a a human activity system, and that defines where we set the boundaries of a family. Is it just parents and children, or is it also cousins and aunts and grandparents and so on? Then we could have a kind of designed, natural natural and designed physical systems that are something in between. For example, a park that is managed by people, that has been designed by people, but then also has a lot of natural processes, or like a fish tank can be a system, and it's partly designed and partly natural. And then completely natural systems could be like the human body, set the boundaries on the skin, or we can even set the boundary on one cell and look at one human cell as a system. And I don't know if anyone else came up with examples that they want to share. If not, we'll move to the next topic, which is moving away from like what is a system to what is systems thinking. And I already said that it's thinking about the world as a system, and it's very different from arguing that the world is a system. It's something that we do to look at it, to make it the complexity more understandable. And systems thinking is a discipline for seeing wholes. It's like a framework for seeing these interrelationships rather than the elements, rather than the things. I think human beings are quite good at seeing the elements and identifying the elements of a system, but really systems thinking focuses on finding the interrelationships, finding the patterns of the system, rather than like getting static snapshots of it. And this quote comes from Peter Senge, who in his book called The Fifth Discipline. And systems thinking can be done on many different scales. Like I said, we can look at the human cell and think of that as a system, and trying to see the interrelationships within the cell. Or the scale can be the human body, or the planet, or even bigger, the galaxy or the universe. So the scales can be very different. And some principles of systems thinking is to consider the big picture, even if it's on a small scale. And then you balance the short and long-term perspectives, recognize the dynamic, complex, and interdependent nature of systems. They are not linear. Those of us who are more engineer-minded, for example, like myself, working with this complexity has been a long journey for myself, moving away from the linear thinking to this complexity thinking. And also, it's more simple to think about the measurable nature of systems, but in systems thinking, we also have to think about the non-measurable nature of the system. So the qualitative aspects rather than only the quantitative aspects. And you have to remember that we are all part of the systems in which we work and function, and we influence those systems, and those systems influence us as well. And this is a very nice visualization from Forum for the Future, originally by, well, this is kind of has been curated by Anna Burney and her colleagues. And at the center of like systems thinking is to find the central purpose of the system, be it like a planetary physical system or be it a human system. And I think one of the most important parts of this this graph is kind of at 10 o'clock. Embrace complexity, constantly learning and adopting. So for those of us who want stability, who want certainty, systems thinking can be like a very difficult concept, even a looming concept for us, because it deals with complexity and a lot of uncertainty. And yeah, this graph was titled by Anna, 10 Ways of a System Thinker. So I won't go through all of the parts, just taking some things that I find most important. Another systems thinker called Leila Akaroglu, she has looked into the tools of a system thinker, and these are now like mental tools. First one we have talked about quite a lot. So we don't just have the animal elements, we also have the interconnections. That's the most important thing to learn to see in a system. Also, linear versus circular, we've talked about that too. So we would like to think of the world as linear because that makes it easy, but it's really a big collection of circular feedback loops of different kinds. Also, for a system thinker, you need to get it out from your silos and get everyone together and seeing the whole picture rather than just seeing parts of it. Another tool for systems thinker is more synthesis rather than analysis. And lastly, there are relationships rather than isolation. At this point, I want to bring an important wisdom from George Box, who says that all models are wrong, but some are useful. So when we deal with complexity and we try to model a system, that model will always be wrong. It will never be able to capture the whole complexity of the system, but they can still be useful. And the level of complexity and the usefulness have to be balanced. For some things, it might be useful to have a fairly simplistic model, a simplistic tool, but it will still be good enough to help us in our decision making. Whereas the more complex models you build, the more realistic they are, but then they won't necessarily be useful. I was saying about like having an engineer mind, which is very natural, for example, for myself. For me, it's more natural to think in a reductionist way and in an analytical way, trying to break things down to their very elements. But when you do that, you won't see the interconnections and you won't see the big picture. And for this reason, we see more system thinkers in the social sciences, because social systems, they defy all the attempts of trying to understand them through reductionism. And because of this, social scientists are often more comfortable with this kind of uncertainty and with this kind of constructivism approach to trying to understand the world. So the idea that the systems that we describe as existing in the world, they are only mental constructs, and we arrive at them through social processes. For those coming from the natural sciences background, this is usually a bit more difficult to come to grips with, to change your perspective from this perspective from the reductionist analytical thinking to the constructivist synthesizing systems thinking. Usually when we talk about systems, there's a very famous iceberg analogy that we only see the tip of the iceberg, and then we start applying our systems thinking tools to try and get down to the very core of the events that we actually see happening. For example, if I catch a cold, that is an event that I see, and then if I I start thinking like, why am I catching a cold? And then I realize, well, when I sleep badly, then I'm more prone to catching colds. But why do I sleep? Or when I sleep badly, I'm more prone to catching colds. So why do I sleep badly? There might be like, for example, stress at work or something else. I don't have time to take care of myself because there's so much work to do. And then what's the mental model below that is that work is an important part of my identity. And for me, work is actually more important than taking care of my own health. That would be the mental model underlying everything. This would be an example of the iceberg analogy in systems thinking. And I would invite you all to try this, but I think for those following, like watching the webinar later, you can just pause the video and then continue once you have tried it yourself. And I think in this webinar now, we'll just skip it for now and continue. Next, I'm gonna go a bit through like different types of transitions. So actually, I'm going to start from the bottom, which is like niche innovations. There are new innovations and radical ideas that can bring about fast change, at least on some scale. But usually these innovations, for them to become permanent or permanent parts of the change, they need these two other levels. The next one being the kind of technical regime of our institutions with rules and regulations, legislations and practices. So for example, in the first step, we come up with an idea for a new piece of legislation, and we start mobilizing a certain percentage of people to go for this change. And actually some research suggests that to actually make a change, you need only about 3.5% of people to join the movement, and you will be able to get it through into, for example, legislation. And then when it's in the legislation, then it applies to 100% of the country's population. But even if you do get the change in the legislation, that still doesn't necessarily bring about kind of deep change in people's mental models. And that change is very slow, painfully slow when you're trying to make transitions come about, when you try to drive change. The last step is painfully slow. So example of a niche, for example, in terms of climate change, they are certain individual technologies, but those might be too expensive for like large scale adoption. But then, of course, with time, it will be able to scale them up, for example, with electric cars. And then the use of electric cars can be pushed forward with this kind of socio-technical regimes. Another example of a niche is, for example, the Extinction Rebellion that is trying to push for radical change fairly fast, because that's what we need for climate change, so that we can slow down and stop and reverse climate change. here are some example of systemic problems. So systemic problems are different from like very clear problems. For example, if something in a factory goes wrong, so the product that comes out from the factory line is not as it's supposed to be, then we start applying our reductionist thinking, and we start going into the different parts of the factory trying to find where the problem is. And this is fairly straightforward. But the systemic problems that we have, they cannot be solved with this kind of reductionist approach. And our big systemic problems that we have, for example, is a failing democracy. This can have different kind of manifestations in different countries. A high rate of corruption in a government can both lead to a failing democracy, and also it is something that can come out of a failing democracy. And the rise of populist politicians is both something that comes out of like a failing democracy and then contributes to it more. So there's a feedback loop in place that we need to address to solve this systemic problem. Racism is also a systemic problem, and what kind of things can be like underlying those. There's like for example, reduced access to education, unemployment due to employer bias, which goes all the way down to the mental models of the iceberg, and we need to be able to address those mental models. We can both have legislation, but we also need to address that. Climate change, of course, that we've been talking about. Climate change is brought about by the disruption of the carbon cycle, and that currently our economic growth is based on fossil fuels still in 2022. In fact, last year in 2021, the 60 biggest banks of the world, they financed the fossil fuel industry with like $2 billion per day. So in this way, you can see where we get the need for systemic change rather than kind of what the discourse has been, that consumers can bring about change with your consumer choices. No, you can't. These banks are financing the fossil fuel industry with billions of dollars per year. So it's difficult to see where I, as a consumer, can bring about any kind of change with my consumer choices. And this is why we need to not focus on consumer choices, but focus on the system, on the feedback loops that keep this trend going. Inequalities is also an example of a systemic problem. So our financial system is such that wealth is concentrating to the very marginal 1% of the population, and this also concentrates power to the same, well, largely the same 1%, which means that we have like this reinforcing feedback loop, which increases inequality that we need to address. And this is kind of the feedback loop that we are trapped in. So you work long hours or several jobs to make ends meet in order to just consume more, be more of a consumer, and with no time left for the things that really matter. And this kind of system we really need to change. There are different kinds of different ways of looking at systems, and they can be thought of as a kind of trying to make sense of different kind of patterns of our world. And here we have like on the right, we have problems or systems that are complicated or clear. So a complicated problem or complicated system is basically something that we can discover. It might have a lot of elements and a lot of interconnections, but we are still able to find those connections. We are able to identify the elements, identify the patterns, and cause and effects are known. In a clear system, these are very simple, and we like these sort of systems because they are simple. We can look at the cause and effect, and things work the way we anticipate. In the complicated system, things do work as we anticipate once we find out all of the elements and interconnections of that complicated system. Unfortunately, a lot of our systems and patterns fall into the categories on the left, so complex or chaos, and these are kind of like very unordered. We can't really identify cause and effect, or we can only deduce them in hindsight. And these are very difficult to grasp with the normal tools that we have that are known to us. So basically our clear system is the known. There are rules in place, the situation is stable, the cause and effect relationships are fairly clear. And for example, we can, like a factory can be in this kind of system, or maybe we can identify best practices that can be applied to clear systems. We can categorize things. Well, then when we move to the complicated one, the complicated is like a known unknown, where we can analyze, we can assess the facts, and we can then apply an appropriate good operating practice, even though we might not know all of the elements. It is possible to still identify the patterns and then apply some best practices. Then we have like the complex system, which is what we are mainly dealing with. In this system, we have no kind of right answers. We can't deduce cause and effect. These kind of systems can't be analyzed in a reductionist way of taking it apart and seeing how it works. It's not even in theory possible to do for complex systems, but it is possible to do it for complicated system. And in this categorization, there's still in the middle, there is this dark cloud called disorder, where there can be many of these different systems interacting. There are multiple perspectives, many different leaders, or many different kinds of rules, and you don't really know kind of which ones to apply. And then as if you're a leader or a decision maker, you kind of need to make sense of it and decide what kind of an approach to the problem you're going to take. Are you going to treat the problem as a clear problem, or a complicated problem, or a complex problem? And if you're in a crisis situation and you have to act kind of immediately, you will have to just kind of act kind of with your gut. You just have to act while you try to keep, if I take, for example, an organization, and the organization hits a crisis situation, as a leader, you have to respond to the situation in some kind of way while trying to keep the organization running, keeping the simple basic functions running. After that, you call in some experts who will try to make sense, who will try to, they use the approach of it being a complicated problem, trying to find the best practice to solve the problem. And then what you need to deal with is mainly people, which makes it a complex problem. So for example, your customers or your investors, and those you kind of keeping their confidence is a complex aspect of this whole crisis situation. So in a crisis situation, you can still apply all of these kind of approaches. What are some of the problems that we need to urgently need a sustainable systems level transition, as some are listed here. You can probably come up with more examples on your own, but again, topping the list as climate change. Actually, I don't have it in my slides, but just this at the start of this year, the World Economic Forum did a risk assessment and risk report on what are the biggest risks in the near and far future. And failing to mitigate climate change is the #1 risk that they see. #2 was extreme weather events, which of course follow from that. And third was loss of biodiversity, which I actually don't have on this list, but could be on this list as well. Okay, we've been looking at system as a fairly kind of up there in the in the clouds, and for having a break, I'm going to go into a bit of an example, a very simple example of how to design on a systems level, how to design solutions on a systems level. So here is an example, clothes dryer. So what we need to do is we need a more sustainable clothes dryer, because we need to reduce our consumption of both material things and of energy. So if you start thinking about how will I design a more sustainable clothes dryer, you might take the existing dryer machine and then start thinking, okay, I will change the materials used in this machine into recycled materials. So we don't use oil-based or fossil-based materials. Okay, we can design all the components to be more durable so that the machine lasts longer. We can make it easy to service so that if one component fails, we can change that component. We don't need to change the whole machine. We can decide not to use any toxic compounds in our dryer. We can like do all sorts of small improvements to the machine. Well, the biggest sustainability issue in the clothes dryer is the energy that it uses. And of course, we can also do design changes to make it more energy efficient. But if we start looking at the simple clothes dryer from a systems thinker perspective, trying to find a solution as a systems thinker, we would want to first look at the world outside the clothes dryer. Where does the need for clothes drying come from? And so we have this kind of, we identify different patterns that, okay, well, why do we need a clothes dryer? Well, we need it because we have wet clothes. Well, why are the clothes wet? Well, because we've washed them. Well, why did we need to wash them? Because they were dirty. And why were they dirty? Because we were wearing them, and so forth. And now if we we can't, the previous solutions were attacking this part of the dryer, which is on the right of this graph, trying to improve the dryer. But a systems thinker would start thinking, well, could we also maybe affect the other parts of this pattern of this circle? For example, could we improve the washer? So if the washer is more efficient, if we can, we could design it so that it mechanically removes more of the water than previously. Usually this would be through the spinning speed. Okay, then not all fabrics can take, say, 1,600 rounds per minute. It degrades the fabric. So that's not the only thing we could do. Well, okay, maybe we could attack the part of wearing clothes. Maybe we should just hang around naked rather than wear clothes, because when we wear clothes, they become dirty and then we need to wash them and then we need to dry them. Well, maybe in some cases a viable solution. Maybe we could attack the part of the dirty clothes. Maybe we can make fabrics that are more dirt repellent so that we don't actually need to wash them very often, or perhaps ever. Then we wouldn't need a washer and we wouldn't need a dryer either. And again, also, if we improve the washer so that it does more rounds per minute to make the clothes mechanically drier, we might need to make the clothes fabrics better so that they can withstand this rotation speed. Or maybe we could reinvent the clothesline. So here is an example, and this is from a YouTube video, which I will then share the details with you in a bit. Maybe, I mean, we used to have the clothesline such that it's outside, but it might not always be practical. Maybe we could invent something completely new that is that utilizes solar energy. Like here in this drawing example, there's a closet that just utilizes the sun automatically. A bit of a clothesline 2.0. So this is kind of an example of when we want to make clothes drying more sustainable, we shouldn't just look at the dryer itself. We can look at the whole system that is surrounding the issue of wearing and washing and drying clothes. I might actually stop here and no, actually I'll do one more slide with you, just on the skills that are needed for making change, and on top of systems thinking skills, of course. You need different kinds of decision-making skills, and in that you can apply systems thinking. Like I said, in a crisis situation, you need to be able to decide how to deal with a problem, what kind of solution you are going to go for, and being able to make right decisions, correct decisions in these kind of situations is very important. So, and when you are not in a crisis situation, then like what kind of decision-making tools you're going to use or patterns at that point. Implementation skills. So once you make a decision or someone else has made a decision, how do you actually bring it about? Skills of being able to apply the decisions, apply different kind of innovations. Learning skills. And learning skills are actually a very important part of a systems thinker, because basically you know that all the time you don't know enough, and you actually cannot know very much, but still wanting to learn more bit by bit all the time is very important. Adaptation and reaction skills. So for example, in the crisis situation, say an organization hits some kind of crisis, how can you adapt and react? And in this, of course, the decision-making skills are important. Cooperation skills, which are very important. So getting multiple perspectives on different kinds of problems. And lastly, anticipation or maybe kind of future thinking skills. So by this, I don't mean, for example, climate modeling or kind of modeling skills, the kind of skill where you are able to estimate what kind of futures are more probable than others, and especially what kind of futures are desirable or non-desirable. So you can, for example, see a trend that's going in a certain direction that is not desirable. You anticipate it and you find the right leverage points, the right points in the system where to interfere and where to disrupt so that you can stop this trend from happening. In the next part, we're going to dive into the climate crisis as an example of a systemic problem and why it is so difficult to come to grips with climate change, why it's why some people are even opposed to the idea that climate change is actually happening or human-induced climate change is happening, and hopefully a few solutions on where to disrupt the different kind of feedback loops in the system. But before that, I think it's good to have a 15-minute break. So it's now 1:25, so 1:40 we would continue.
There we go. We are recording again.
Okay, so let's continue with how the climate crisis is an example of a systemic problem, why that is, why it's so difficult for us to grasp it and find solutions to it. I'll start by saying that environmental policies have succeeded in addressing many of the most urgent environmental problems. For example, we were able to tackle the destruction of the ozone layer, but in that case, the problem was fairly clear. It was caused by only a few chemicals that were used by only a few companies. So even though it's sometimes compared to like, oh, we solved the ozone problem, we can solve the climate problem, but they are in some ways very, very different types of problems. Environmental policies have also addressed kind of a lot of different kinds of emissions, but they have fallen short in tackling the global big environmental problems, wherever emissions come from many different sources and are then spread all around the world. Our environmental policies, even though we have tried, we haven't tried hard enough, and we haven't been able to solve the problem that we have. One of the kind of what would I say, like the top of an iceberg, or kind of like this quite a lot indicates the problem that we have. Our car system has an overall efficiency of about 1%. I don't know which company in the world would accept an efficiency of 1% in their functioning. Most of the times, cars just sit there and use up urban urban space and are not doing what they're supposed to be doing, which means transporting people from one place to another. And also, even though we have managed, for example, in many European countries and in Finland, we've managed to reduce carbon emissions in a lot of sectors. Car use or our transport system is something where we have not been able to cut emissions. The second thing to take away from this picture is that we can't, the solution is not to improve efficiency by 10%, which is a lot of the times the solutions that we apply, is that we improve efficiency and then the efficiency improves by 10%, or something like this, 20%, or some other percentage. But the efficiency of the car system is currently just so low that what we need is a very, very, very drastic change to make our transportation system sustainable. And it means that the role of the car in our transportation system should be played down a lot and replaced with other means of transport, or at least the role of the car as we know it now has to be drastically changed if we want to achieve sustainability in the transportation sector. Okay, so why is it so difficult to comprehend and reverse climate change? The people who don't really understand climate change, they tend to lack the grasp of how a complex system works. Any system that is like sufficiently complex, much of its behavior is counterintuitive. For example, in climate change, how can a gas that forms such a tiny, tiny fraction of the atmosphere have such a large effect on the climate? Because we can't really grasp the quantity of energy that the Earth receives and then emits back into space, that even like the tiniest imbalance in the tiniest gas can really disrupt the equilibrium in a very, very drastic way. And this is fairly difficult to comprehend. But there are other reasons also. Our technologies that we enjoy using every day, they tend to magnify the power of our capabilities to alter the global environment. So in the past, human activities were able to disturb only our immediate environments, and our influence was not very far spread, which is very different from today. Today, we are able to spread our influence and our emissions globally. They are found in the furthest corners of the planet, and the technologies that we use today, they make this possible. And our influence is spread far and wide, also in that where a product is used can be very far from where it's actually produced, and even like through the supply chains, many components are produced in many different parts of the world. And at the same time, it's very difficult for us to see our influence and pinpoint where our influence actually is and what is our part in it. Climate change is only loosely linked to where in the world the emissions occur. Well, basically meaning that the biggest effects of climate change are felt in, well, it happens to be in this case that the biggest effects of climate change, the biggest reduction in, for example, quality of life, are in the places which are actually not emitting as much or consuming as much. Here in Finland, where the average consumption is about 4 times the sustainable rate. Climate change has not really affected our everyday lives, whereas it has affected everyday lives in places which are experiencing more extreme weather events, heavier rain, more floods, dry summers, fires, these kind of things. I think only in the recent years we're seeing these effects also in the countries which are consuming the most. So, for example, forest fires in California, in Australia. Last summer, there were big floods in Central Europe, and it did not trigger that much of a discussion about climate change as I would have thought that these extreme weather events would have. So still, even now that they are hitting close to home, not perhaps in Finland, but in other developed countries, still there is big climate denialism going on. And all our greenhouse gases, they accumulate in the atmosphere, they circle in the atmosphere regardless of their point of origin. And this makes it even more complicated that actually the point of origin of the emissions is different from where, for example, the reason for the production is. So the reason for producing a product is the demand of a developed country, and then the product is made in a developing country where the emissions occur, and then those emissions circulate around the globe. The effects of the emissions persist for a long time. So greenhouse gases have different, they persist for different amounts of time in the atmosphere. And we have some greenhouse gas emissions that are in a human scale pretty much permanent in the atmosphere. But also like, even if it's not, it only persists for a certain time, it still accumulates in the atmosphere. And even if we would stop emitting greenhouse gases right now, the emissions that we have already made, the effects of those will persist for a long time. So if you make if we somehow manage to get to net zero emissions, say tomorrow, it doesn't mean that the extreme weather events would stop tomorrow. And if this, of course, would then make some people to say, hey, look, we stopped all the emissions, it still didn't help. And this is for this reason that the effects persist for a long time. And also at the moment, no human technology currently exists to remove greenhouse gases from the atmosphere that we could use on a big industrial scale to take carbon from the atmosphere. There are some technologies in the making, but and many of our climate scenarios are based on the fact that we are going to find solutions. We are going to come up with technologies that sequester carbon from the atmosphere, but currently the only large-scale solution we know is trees or forests or various kind of vegetation. And unfortunately, we are destroying the planet's potential of sequestering carbon from the atmosphere through deforestation. And like I said in the beginning, our abuse of the Earth's carbon cycle, i.e. use of fossil fuels, is what makes the current global economy possible. And fossil fuels are what we think of like business as usual. So kind of alternatives may be unimaginable to many people. Like they cannot imagine an alternative to using fossil fuels. And at the same time, we just cannot take for granted that we can continue this way of life, or it will have severe consequences. So on the planet scale or on the atmosphere, in the atmospheric system, we are stuck in a or in this carbon economy. We are stuck in a, or on the trend of a reinforcing loop that's currently getting out of hand. And then on the other hand, in our mental models, we are stuck in a balancing feedback loop where we kind of remain in the status quo. And a lot of effort is put into like getting out of the status quo. But as you can see, this system is very resilient to change. The fact that our global economy is so tied to carbon emissions, there are several different systems and several different feedback loops, which make it really, really difficult to disrupt this system. The concentration of greenhouse gases in the atmosphere is the world's largest and most complex collective action problem. And this is something that I encounter a lot when I talk. So people say, oh, but Finland can't do that much, or Finland is already doing enough. On that note, I can say that Finland is not doing enough, even though it may seem that Finland is doing, and we have a lot of promises, but in the end, in Finland, consumption still is about 4 times the sustainable rate. So Finland is not doing enough. And then others are saying, well, should Finland do something if China is not doing anything? And this is the problem of a big collective action problem. We need absolutely every person, every organization, every country on board to solve this problem, to make actually a big system change. And I think the problem currently is that many actors and organizations and even countries are on board for making small changes, improving energy efficiency, improving material efficiency. Those are things that also are kind of economic questions. So reducing energy consumption also reduces costs. Same thing with materials. So it's kind of easy to make those kind of small solutions. But what we really need is a big system change. And actually, what it seems like at the moment is that no actor, no organization or country is ready to make that big of a change. And everyone is waiting for someone else to make the first leap. And which means that we're kind of in a stalemate situation with trying to solve the problem. And lastly, the effects of climate change are so huge and so pervasive that we cannot even imagine how large the consequences will be, how far into future generations those effects will take place. And I think a lot of people get this kind of mental block when the changes are just so huge that they can't even really be comprehended. At the very start of this webinar, I showed you the global temperature in the last 542 million years. And according to scenarios, various different trajectories, we are on track to look at temperatures that humanity has never faced before. And this is just something that is so difficult to comprehend that it actually stalls our thinking. And here is maybe kind of the situation we are in. We have a lot of different barriers that make it difficult to move. We have a balancing feedback loop on the status quo in our mental models. We have a reinforcing loop on the carbon emissions, and we have a balancing loop on the status quo. And in the beginning, I said we need balancing loops, and that it's good to talk about balancing and reinforcing loops with these terms and not as positive or negative, because in this case, the balancing loop is a negative one. The balancing loop that keeps us in the carbon-based economy. And we have so many different barriers that keep the existing system in the place. This is actually true for most systems, that the system designs itself in a way that it's difficult to change it. Humans make this possible. I don't know how it's like deep in the human core to resist change, that being one of the biggest barriers to actually being able to disrupt a system. Existing legislation can often constitute as a barrier to change, because regulations are kind of tuned in for the existing regime. So that means that sometimes it's very problematic or even illegal in some way to push for a certain kind of change. For example, for a long time, for restaurants, selling out surplus food was illegal because of the hygiene legislation, which has now been changed, fortunately, so that restaurants can sell out their surplus food. But this was not possible before. And if restaurants did sell their surplus food, instead of throwing it in the bin, they were doing illegal things, which made it problematic. Or then selling insects as food, another thing that was not legal still a few years back. And I remember trying insects as food in one of the restaurant days, and it was very exciting, and also like exciting to have this kind of new type of food, and then so weird that it was actually illegal to sell that. Also, selling carbon credits has been illegal. This was in Finland, just solved this year. An organization called Compensate was selling carbon credits, and in the eyes of the law, they were not selling a product or service. They were just collecting money, which meant that they should have had or complied with this money collection legislation. So these are like examples of how legislation can be a barrier to change, but also like when you are able to change the legislation, you are kind of tapping into the systemic nature of the problem. Also, interventions that we have done have thus far focused on marginal technological improvements and efficiency gains, like I said before, energy efficiency, material efficiency, which improve by X%, which is usually not a very big percentage. And they are usually driven also partly by kind of financial and economic incentives. So another example is that the average carbon footprint of a Finnish person is 10 tons of carbon dioxide equivalent. And then you can bring it down by maybe a few tons. You can bring it down to 4 tons if you make really big changes. But what we need is it needs to go down to 2.5. It needs to be cut by 75%. And actually even further than that, like in 2050, it needs to be like less than 1 ton per person in the world. So the reductions are so huge that these kind of marginal technological improvements are not going to help. And major transformations are needed in the key production and consumption systems. So our ways of producing and consuming energy, food, mobility, housing systems. And because these are the result of like complex interplay between a lot of different factors. And we still need to meet society's essential needs. These systems are like a massive burden on the environment, and they extract our resources and produce waste and emissions. So how do we bring about change with policy? This is now focusing on policy, and this is from Lorbach 2015. So from a policy perspective, when you want to enable systemic change, you need to focus on a broad policy mix. You need to start with promoting innovation and experimentation. That's like on the left of this this graph. And then from that, you need to come to kind of the destructive, well, in the first part, you need to, with legislation, make the unsustainable modes of producing and consuming, you need to make those less and less incentivized. And this can be done with several different measures. You can make certain chemicals illegal to use completely, for example, or then you can give financial incentives for sustainable products and services. And what you can do to dispromote unsustainable modes of producing and consuming can be with, for example, strict regulation, like saying this chemical is no longer allowed, and all companies will have to find an alternative to that chemical. So that's kind of stopping the unsustainable things. And then you need to promote the sustainable things, which are the green, which is the green part of the graph, which is then promoting innovation and experimentation and enabling new ideas to spread, and working on both of these two modes. And also you need to remember that different kind of policy interventions, they generate winners and losers. And of course, those who see themselves on the losing side of a certain kind of policy intervention will, of course, resist that policy with fervor. And this is also kind of a balancing loop that exists. It will challenge jobs in a way that also might make it might make politicians kind of scared to bring in certain policy interventions, because always someone will lose jobs, someone else might gain jobs, but that might not be the same person. So if we say that, okay, the green economy will generate this many jobs, it also means that this many jobs will be lost. And these people who lose their jobs are not necessarily the people who are going to gain jobs, which means that these people are going to resist change very strongly. And maybe these kind of vested interests are one of the biggest obstacles for change, because those companies who will not benefit from the new policies, they will oppose them strongly. And if those companies are very powerful, they may be able to stop these policies from coming into practice completely. And public authorities have a range of instruments at their proposal, but usually public policy is geared towards kind of like short-term objectives, which means that the kind of big change that is needed in the coming decades, it's very difficult to gear the whole system into going towards that change. Examples of the instruments that are available are, for example, environmental standards and requiring organizations to comply with these standards. We can encourage or discourage certain practices through taxes or subsidies. Yeah, we can have complete like bans on certain things, and all of these will need to be used. Sometimes it might be that one certain policy instrument is hailed as this is the way to do it, but usually that's not the case. Remember that we're dealing with systemic problems, so there is no one tool that will solve it. And the kind of transition that we're going for is it's vague and it's very much in the future. There are long-term objectives beyond the lifespan of our current politicians. So that means that they might not feel the urgency to use all of the instruments that might be in their at their disposal. Yeah, so I jumped into this point actually already, that transitions are about more vaguely defined distance objectives, whereas our policy is usually geared towards like clearly defined close objectives. Okay, so bringing about systems change. So what to do, where to interfere, where to put our resources if we want to make system transition happen. And Margaret Mead, she has said this famous quote saying like, "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." And indeed, there are many examples of how the power of people has been able to bring about change that we want to see. And I think I mentioned this earlier today, the 3.5% rule. So you don't need to get everyone on board to put a big chain reaction in motion, according to research. Now I have lost the author, Erica Chenoweth, who's a political scientist at Harvard. She found that the kind of civil disobedience or these campaigns that are driving for change, they were most likely to succeed if they were non-violent and they went over this threshold of 3.5% of the population who came on board to make the change. And also the research points to kind of non-violent rather than violent protests. So non-violent campaigns were more efficient, about twice as likely to succeed than violent campaigns. So if you want to make sustainable change, it has to be non-violent. One example of this is called the Singing Revolution in Estonia, where through this kind of positive thing of singing, people came together and wanted to leave the Soviet Union. And yeah, this is called the Singing Revolution. And about 3.5% of the population participated in it. I don't know if you're familiar with the handprint footprint idea. Basically, what brings about change is your handprint, or an organization's handprint, how you affect the world positively. So if you only focus on your own footprint, you are not you're going to be able to change your own organization, but you're not going to be able to bring about systemic change. So if as an individual or as an organization, you want to bring about systemic change, you have to focus also or work also on your handprint and not only on your footprint. So your footprint is basically your own, if it's a carbon footprint, your individual carbon footprint is a certain size, say 10 tons per year. And it's important to reduce your footprint to be an example and to actually live your life according to your own core values. Because if you make choices that do not align with your core values, then it will affect your own well-being. And similarly for an organization, if in your core values you have some kind of sustainability values, but then you don't do any measures to reduce your own footprint, then you will be greenwashing and you won't be able to attract the best employees, for example. So yeah, next step from your own footprint is to be an example to others. So you do have to reduce your own footprint, but you also, as an organization, you have to do more than that, because if you are trying to reach out with a sustainability agenda, the first opportunity when someone finds out that actually your own footprint is pretty high and your company is doing nothing to reduce it, you will be accused of greenwashing. So you do need to focus on your footprint, but that is not the biggest thing that you can work on. So you can start by increasing your handprint by being an example to others. Other companies in the same field as you, for example, they see that our competitors are going this way, we probably need to as well. Then the next step is kind of active actions. If being an example is just like a passive thing, not doing active things, the next step is to do active things. For example, teaching, communicating, you have campaigns, you have anything that's kind of, they're active, but they're in one direction. So for example, your organization communicates outwards, or for example, here I am teaching systemic change to you listeners. This is part of my handprint, but I can also do more. This is just a small part in bringing about systemic change. The next step is bigger sustainable development projects, enabling others. So if after this lecture, you go to your own organization and start changing things to be more sustainable, my handprint grows through your actions if I have been able to spark some kind of good snowball effect. Enabling others to reduce their footprint, enabling others to increase their handprint, helping others to organize campaigns. This is the next step of the handprint. Or trying to affect legislation that affects your business. If you're familiar with the United Nations Global Compact, in those rules, the organizations that participate in the Global Compact, they have to support new initiatives for legislation that takes that sector into a more sustainable direction. So they have to view change towards sustainability as good. So it's not enough just to comply with the current legislation. You also have to embrace in a positive vibe new upcoming legislation that might make your work again a bit harder, but it will make your business and your sector more sustainable. So these kind of things are on this level of your handprint. And also working together with your production chain. So in the previous level of the handprint, you can have in your organization, you can have like procurement rules that say that we only buy from producers who have a some kind of sustainability certificate, for example. But something bigger would be to work to constantly together with the actors in your production chain to make also their part more sustainable. So if something unsustainable is found in the production chain, the organization wouldn't kind of stop buying from them or boycott that organization, but together start working to solve those problems. And with this, we are able to bring about a bigger systemic change. At this point, you could, for example, tell an example of a handprint action, either your personal handprint or of your organization. And this exercise could take 5 to 10 minutes. But again, I think we could, in this section of the webinar, just continue. And if you're watching this on like the recorded webinar, you can stop it now and then try to think of some kind of handprint action that you are doing personally or your organization is doing. For example, in my organization in Sykli, me being here teaching is both part of the organization's handprint, but it's also part of my personal handprint. But I think in this case, we will just continue, and that's something for you to perhaps think about later. So we've talked about systems quite a lot today. Maybe a few words about what transition means, or when we bring about system change. If we want to make system transition, we've now looked at what the system part means, and now a few words on what the transition part means. And here's a quote from Elzen and Wieczorek. In a transition, both the technical as well as the social dimensions of a system change drastically. And this means that the transition does not mean incremental technological progress, which is very much what some people view it as. It's technological and social, very much actually social, and it's drastic, not incremental. This is an idea that I touched upon a bit earlier on this webinar. I can see myself jumping ahead of myself sometimes when I get excited. So thinking about what kind of futures we want, what kind of futures are possible. Some futures are possible, some are impossible. What futures are probable? For this kind of thinking, for example, this statistical analysis can help us, or modeling can help us. For some parts, it cannot help us. With very complex systems, such as human systems, we don't even know what is possible or what is probable. But on top of that, thinking about what kind of futures we want to make, what kind of a future we want to make as individuals or as organizations, what kind of a future is desirable or is undesirable. Because in essence, the future is made. It's not just something that comes and happens to us. It's something that is made, and it is built on actions of today. So the actions of today build the future, but also the thoughts that we have about the future right at this moment also affects our actions of today. So there's kind of loop here. There are many possible futures. Climate models give us some kind of possibilities. And in this case, now that we said what kind of futures are possible or probable, a future where no climate change happens is impossible. So maybe it is not worth our time to try to bring that kind of a future about. A future where we limit global warming to 1.5 degrees Celsius, which is what you see quite a lot, is quite improbable in the face of, like, from what we gather from the research that we have available to us, the 1.5 degrees warming is slipping away from us quite far. What we still can do is limit global warming to 2 degrees. This still is possible, but will require a lot of action. Currently, we are on the trajectory of like going towards a warming of about 3.5 degrees. And again, I'm saying like this doesn't sound like a big increase, but it is a temperature that humanity has never seen before. So we don't really know what will happen. For a systems thinker, being able to think about, to practice future thinking is also very important. And I'm going to show you a very simple exercise that can be done for, like, in terms of futures thinking. It's a exercise called what if. And the aim is to come up with sentences that start with what if, and then something that might happen in the future. And then you start from that point. What kind of a world would we be in if a certain thing happened? And again, I will leave you to think about this on your own. If you want, you can pause the video. Here are some examples of what if questions. What if robots will do all of the work in the future? And then you start imagining a future from that perspective. Or what if we are able to reverse climate change? Previously, I said that according to our research and calculations, reversing climate change is not possible. But what if it was possible? What would happen and what would the world look like? What if we lose all of our birds? What would happen to our ecosystems as a whole? What if we did learn to live with less? What would the world look like if this came about? And then a what if concerning my organization, for example. What if Sukli was able to consult all of the Finnish companies on sustainability? What would the world, or what would Finland look like in that case? So think of a question that starts with what if, and it can be related to your organization or just kind of future as a very distant thing. And usually actually when we do this futures thinking, it's easier to take a future that's quite far away. So if we start thinking, what would the future look like in 5 years? We are usually very tied to the realities of today. But if we start thinking, what would the world look like in 2100? Then we can really detach ourselves from the constraints of today. So yeah, I had this exercise of sharing it in the chat, but we'll just skip that for now, and hopefully you can come back to this, or maybe use this exercise within your organization, for example. Okay, working with the future. this is from Future Stewards, a report called 10 Tools for Systems Change to a Zero Carbon World. So now we're going to go more towards from theories to perhaps a bit more practical tools. And on this chart, you have different tools that deal with uncertainty and with agency. So on the x-axis, we have uncertainty, and on the y-axis, we have agency. And on the bottom right corner, we have, for example, forecasts. For example, climate models fall into this category. And even though even the climate models have a lot of uncertainty, they have relatively little uncertainty. They still have, like, they are very complicated, but we might not know everything that's going on in this complicated system, but it has relatively little complexity. So it does have, it is complex, but it's not as complex as, like, for example, human systems. But this kind of the forecasting work doesn't really give much agency to people working in it, and like we've seen that actually dealing with climate change and other systemic problems, they are very much linked to the human mindset and really need especially social change. So we are quite good at bringing about technological improvements and technological change, but what we really also need to step up the gear is on the human change. And these kind of forecasts don't really give much agency to a wide range of people. But forecasts are very useful tools. Governments and businesses make these quantitative forecasts based on past trends or maybe some modeling. And they do work to some extent as well, but then something unexpected might happen. So, like, for example, the COVID pandemic is something very unexpected that disrupted everyone's forecasts. So these are not very good at handling kind of qualitative uncertainty. Then if you take roadmaps next, they are usually kind of based somewhat on, or they can utilize forecasts, but they are better tools when you have a lot of different shareholders, a lot of different stakeholders and players. And then these are good for also finding emerging opportunities, because the point is to bring people together. And it's a way to coordinate the actions of many. So usually roadmaps would be for a whole sector, for example. And a whole sector might have lots of different kind of businesses working within that sector. And then you'd have a common roadmap for the entire sector to follow. And also these roadmaps kind of go through certain points. So if you think about, for example, mobile communications, you start with, actually, this is a poor example because I don't actually know how mobile communications, how the history started, but basically you evolve from previous to 3G to 4G to 5G and so on. So this is a very kind of roadmap type of advancing in a certain sector. Then you have scenarios on the top, on the bottom right, and the scenarios with the scenario tool, what we try to do is organize our thinking around a small number of major uncertainties, and then we create stories or scenarios or about what those worlds could look like. And this is how this systems thinking is linked to futures thinking. So if you want to use this kind of tool, you need to be able to do some futures thinking to come up with these scenarios. And it might feel actually difficult at first to come up with these stories, to come up with these scenarios of the future, but it's a skill, and it's a skill that can be learned. It's a skill that if you've never done it, you won't have it. And you have to start somewhere, and then you start practicing and you will get better at it. So creating these stories around certain uncertainties, but of course you will need to come up with those uncertainties. And those uncertainties will have to emerge from somewhere. So now that we have had this pandemic, we might be able to better come up with scenarios of future pandemics and how they will affect the world. And then the last tool is called Pathways on the top right. And kind of climate action needs all of these tools. We need to have like this clear directional intent of the roadmap tool, but we also need to be able to handle uncertainty and learn fast when unexpected events do occur. And the pathways usually have three different, when you think about the pathways, you develop three different paths called horizons, and I will show you later in a bit how to make those horizons. And these horizons will kind of hold together all the tools that we need for the future that we want. Just a few words on like how to bring about systems change. So we were talking about the balancing loops. Here they are called ambition loops. So find the loops that actually hold those things in place that actually need to be held in place. So in this case, what we might want is a stable climate. Okay, that's a bit of a big example, but we want a stable climate, so that we would need to find a balancing loop with that. Some things can be exponential. For example, setting exponential goals. In some way, I disagree with this this set of tools. Like I said, exponential growth is not possible to sustain for a long time. So set ambitious goals, I would say. And then bring everyone together in a way that everyone can see their own path in getting to the same goal. One last thing that I will introduce before going into the bigger exercise that you can do at home relating to systems thinking is leverage points. So leverage points are the points where you can enter the system and bring in disruption or bring in change. And leverage points have different strengths. So, and I'll start from the least effective and then save the most effective to the last. So the first leverage point is parameters and numbers. Taxes, subsidies, standards. These are a very good leverage point. And in terms of bringing about change, they are relatively easy to kind of target. For example, we could have air quality standards that are at a certain level, and then you can increase that standard, or you could have a minimum wage that's at a certain point to start with, and then you increase that. Or well, anyway, this is like kind of the rules. If you think about a football game, you can change the players, you can change the rules, or you can change the goal of the game. And of course, this has like very different effects on the system. And these parameters and numbers are a fairly small part. So this is where you would improve one player's efficiency, for example, in a football game. People care fiercely about these parameters and try to attack these to make change, which is very good because they are kind of one of the easiest targets. But these rarely change behavior. Like has been discussed, this is very much a human problem, and at the bottom of the iceberg is the human mindset, the certain ways of thinking that are really, really deep, and changing the parameters will not change the way that we think. The next leverage point is buffers. Buffers are something that stabilizes a system. So you have some inflows into the system, and then you have outflows, and you might have a stock within the system. And we can use buffers to our advantage. For example, I can't remember where I took this example from, but the soils in the eastern United States are really sensitive to acid rain because they don't have a big buffer of calcium that would neutralize the acid. Then in the west of the United States, there's the soil contains more calcium, so which acts as a buffer. So this buffer gives us time to deal with the problem of acid rain. Whereas in the east, the soils didn't have much calcium, which means that negative effects are felt quite fast. If a buffer is too big, the system gets very inflexible because we don't realize that change is happening, and the buffer is kind of preventing the effects from being seen. And if the buffer is too big, we'll create a lot of damage before we actually see the damage, and the system reacts very slowly. But then if we have a very small buffer, it fluctuates a lot, and we don't really have time to react and correct our actions. So for example, with climate change, the ocean is a big buffer that has been slowing down climate change or global warming for a long time. And now that buffer is coming to its end, and we have not experienced the effects of climate change for a long time because the ocean has been acting as a buffer. Number 10 in leverage points is the structure of material flows. So from here, I'll give an example of when the Hungarian road system was laid out in the capital city Budapest. The traffic went kind of like from one side of Hungary to the other, and it passes through the center of Budapest. And that meant that there was a lot of air pollution and commuting delays because the major traffic went completely like through the capital city. And this is not easily fixed. So You can, for example, try to reduce emissions by reducing speed, but then it causes congestion, which increases emissions. So basically the only solution to this is to kind of go make a different route for the material flows, basically to rebuild the road system. And while this can bring about big change in the effects, it also needs very big inputs. So when something is kind of laid out in the wrong way to start with, it can be very difficult to, you cannot really improve the system. You have to like take away the old system and put a completely new system in its place. Delays are one leverage point that we can use to our advantage or not. So if you're taking a shower and the heater is in the basement and your shower is on the 4th floor, if you put up the heat in the basement, it will take some time before it reaches the 4th floor for you to have a shower. And while you're waiting, you might think, oh, this is not working, or actually I turned the button in the wrong direction. So you turn it back, takes some time for the information to go down to the heater, and then again, the heater to bring, to change the temperature of your shower. So delays are a common cause of like oscillating patterns in the system. So if you're trying to adjust your goal, but there are a lot of delays, you'll get a lot of like overshoots or undershoots. For example, from the time that a pollutant is dumped on the ground somewhere, and then there is a delay before it is measured in the groundwater, and someone goes like, hey, there's something in the groundwater, something happened, and then you try to trace it back. That's a delay that can, well, again, it can give you time to deal with the problem and prevent it from going further down, but also it's something that makes it more difficult to pinpoint the actual problem. Then keep or break balancing feedback loops. And this is much more difficult than it sounds. So like I said, there is a balancing feedback loop that is keeping in place our carbon-based economy, and we need to break that. We need to break that if we want to bring about systems change. But how do we do it? I don't have the answer. We would have to identify more closely the parts of this feedback loop and then decide which part of the feedback loop we could most efficiently disrupt. Or then again, we might want to keep some kind of balancing feedback loops in place and protect those. For example, our ice caps are a kind of a balancing feedback loop. The albedo helps with mitigating climate change. So what we really want to do is keep those ice caps somehow there, even if it would happen artificially. Also then driving the reinforcing feedback loops if such good feedback loops exist. And for example, the reinforcing feedback loop, so feedback loops, reinforcing feedback loops they are big drivers of change, but if they are negative, they need to be stopped. And that can be very difficult because they are, as the name suggests, reinforcing. And but if they are good, we can kind of try and add more fuel to that. Number 6 is structure of information flows. So how to have the correct information at the correct place. For example, having electricity meters somewhere where the habitant can see it. For example, they see the electricity meter every time they come in, every time they arrive home. They see how much electricity is being used. This kind of information flow then can induce change in behavior, rather than this kind of source of information being, for example, in the basement, and you need to go specifically to check your electricity meter to see what it says. Whereas if you see it kind of all the time, then it can create a new loop, feedback loop, that can then bring about change that we want. The rules of the system, the incentives, the punishments, and the constraints. So like I said, in the game of football, we can change the players, but the game is still the same. So then we can decide to try and change the rules of the game. For example, in football, when you throw from the sideline, you have to have both feet on the ground. And you can't have one foot rising off the ground when you're throwing from the sidelines. And this is kind of a rule of the system, probably was brought in at some point. And it does change the game a little bit for some parts. Maybe on a more system level, constitutions are one of the strongest example of kind of rules of the system. Then we also have unwritten social rules, which are also kind of part of the rules of the system. Yeah, trying to change the rules is one way of influencing the game, so to speak. Next is the power to add, change, evolve, or self-organize the system structure. So one of the most kind of stunning things that living systems can do is kind of change themselves utterly, kind of from the bottom up. You have whole new structures or whole new behaviors that emerge. On the large scale, you can see this in evolution. Like the environment changes, we have new species that emerge through evolution. And we can also have technical evolution, we can have social evolution, but this idea of evolving somehow, the system itself has the power to evolve, and then you can nudge that evolution into a certain direction. And self-organization means that it rises from the whole system of itself somehow. For example, you can use a leverage that has been further down this list, and then you have completely new behaviors emerging from that change. And being able to self-organize is a kind of the strongest form of resilience that we have against, while adapting to climate change. If I continue on this football analogy, you can change the goals of the system. So far we've changed we've improved players, we've changed players, we've changed rules. But if we change the goal of the system, the goal of the game, then we bring about actually drastic change, which is what we're trying to get to. And running up out of time a little bit. Next one is the mindset out of which the system arises. So now we're getting to the bottom of the iceberg, the big shared ideas of the society as a whole, the big assumptions that we have about life, living, like big assumptions of the way we should be doing things, kind of paradigms that are society's paradigms. Changing those paradigms is of big importance. If we manage to do that, then we will be able to bring about system change. We can do all of the things that are have been previously stated as leverage points. But when we get to this bit, if we are able to change the mindset, the paradigm, then we can bring about big change. And then number one in this tools list is transcending paradigms, because we like to cling on to paradigms. They give us structure for our thoughts. Being able to let go of those can leave us space for even bigger change. No paradigm is kind of true in itself. So if you think about the iceberg, or you can think about the football game analogy, what kind of points of entry do you see for solving a certain problem? Okay, 2 exercises that you can do after this lecture. One is kind of a very basic systems thinking exercise of constructing a causal loop diagram. And it's a visual aid of the elements and interactions within a system. So this exercise can be useful on its own, but it's more often used as the first step for more kind of in-depth analysis of a certain system. And there's in the causal loop diagram, you kind of identify certain elements. So usually it starts by adding elements. Some things come very naturally and some things don't. After you've added a certain amount of elements, you start thinking, now this is getting out of hand. I need to start thinking of system boundaries. So I will not include this element in the system, or I will include this element in the system. Once you've identified the elements, you start putting in the interactions. And this is one of the rules of a causal loop diagram. The arrows, one arrow always goes in one direction. So here, burning fossil fuels, if you increase fossil fuel burning, it will lead in a higher concentration in the greenhouse gases of the Earth's atmosphere. And what kind of elements you usually have in a causal loop diagram, they are specific elements. So for example, increasing greenhouse gas emissions is not an element. That's kind of like a dynamic thing. So try to make all the elements kind of static, and then we bring the dynamics in with the arrows. And so you can have, for example, economic growth that leads to increased, sorry, I'm jumping ahead. So also try to think of the steps that go in between. So you have economic growth, which, as we have observed, leads to an increased greenhouse gas concentration in the atmosphere. But of course, it's not as simple as that. Try to do it in the different steps to see how the system actually works. And then once you start seeing different pathways, you start seeing the different loops. This picture is kind of putting the previous one together, and you can see that you have a reinforcing loop of the fossil fuel burning and the demand for energy, and then the balancing loop, which has not quite kicked in yet, which is like fossil fuel reserves will diminish and then increase the price of fossil fuels. And these reinforcing loops cause this exponential growth, and the balancing loops cause this kind of equilibrium. In reality, this is what we see. So systems are a lot more complex. This is an example of a causal diagram about wind power and how to increase the potential of wind power. This is another example that I did with one of my study teams on how climate change will affect chocolate bean production. And in this case, we actually ruled out the climate dynamics from this system, and then just took that for granted, and then took those outputs into this system of chocolate bean production. There is an app or an online tool called Online Visual Paradigm that you can use to construct your causal loop diagram. It's a big help. The second exercise is 3 horizons. So in 3 horizons, you, as the name implies, you come up with 3 different pathways. Usually the colors are so that there's a green, a blue, and a red pattern. And the horizon 1 is the dominant way in which things are done now, and they show signs of strain and lack of fit to the future. So, for example, fossil fuel burning, which is the business as usual, does not fit into our future vision. Horizon number 3 is how we want things to be in the future. So the vision that we're working towards. And then horizon 2 is kind of like a transition horizon. And it's something where you have innovations that help make this desired future a reality. And how to come up with the 3 horizons is you do a mapping process. You first go through the horizon 1, which is your business as usual, and come up with evidence that you see that suggests that the current system is not working. It is under strain. It doesn't fit, for example, upcoming policies. It doesn't fit societal requirements. It doesn't make use of the emerging knowledge, and all in all is failing. And then, of course, thinking, what is keeping this current system in place if it is failing so drastically? Then the horizon 3, what are the visions for the future system? What values and norms would support it? What long-term trends are driving towards these changes? What kind of feedback loops should be created or disrupted or weakened or strengthened to bring about this future? And what kind of examples do you know where the elements of the future systems, elements of this already exist? Is someone else already trying this out? And how are they doing it? And then mapping number 2, what innovations do you know about? So these are something that already exist that might be good growth points to bring about the horizon number 3. So technological innovations, biological innovations, social, legal, political, these kind of things are then part of the horizon number 2. And I'm now 3 minutes over time, but that was my part of the presentation, and here is a more detailed, if you want to think about as homework or an exercise that you can do related to systems change following this webinar.
Okay, thank you, Aura.